Okay, folks, well, I think we'll go ahead and get started. It's good to see you all. I'm looking forward to another time where we can get together, get into some interesting topics, and also, since it's a Thursday, we'll have a little bit more time for a lab type of environment. So let me go ahead and open us up in prayer, and I'll give you a sense of the things that we'll be covering today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course. Lord, I pray that as they're looking at completing their time here at EPU, that all of the skills and things that they have been able to get familiar with will help them in getting the job that they would like. Pray that the material on system engineering will be something that could, in a sense, give them a little bit of on-the-job training as well as just learning some more skills. Also, please help them in their spiritual formation, Lord. Help them to really drink deeply from all the things they've learned from Scripture, all of the theological concepts that they've become aware of, and give them the tools that they can be applying these principles in all areas of their lives, both now and the future, and give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, what we're going to be talking about today is we're now in the second chapter that's dealing with the engineering development, and this is where you get into the depths of completing the design. So we spent a lot of time talking about the concept development. Now we have 5 chapters that we're going to be focusing on the engineering development. So we talked about advanced development, and I tried to give a couple examples, thinking in terms of the James Webb Space Telescope. And for this lecture, we're going to be talking about software engineering. And the authors actually have a nuance about this, that there's actual 3 levels that I'll be showing in a couple charts to give you a little bit more of a perspective. And so there is a course that I teach on software engineering. And so that's something that I'm familiar with, as well as system engineering, but there's going to be yet some more divisions that we'll see here. And so this is the first chart that gives us a little bit of a heads up on that. So they talk about this idea of a software engineering versus a software systems engineering. And so these are 2 terms that are not synonymous. And so they want to make sure that we're aware of that. So software engineering refers to the development and delivery of software products, standalone or embedded. And so the focus is definitely on software, but you're using an engineering sense to making sure what you're doing. So it's not just writing code, it's thinking of all of the things that's going to make it serviceable, maintainable in the intended environment. Plus, there's also software systems engineering, which refers to applying principles to the software engineering discipline. So you're applying system engineering towards software. You can be thinking about that. And like I said, we'll have a chart in just a minute that will give you some perspective on that. So how do we define software? We can think of it in terms of 3 major components. There's the actual coding or instructions that are done. There's the data structures. That's another course that I teach, and how we start to put all of the things that we're trying to quantify into logical structures or containers or things like that. And plus, there's the documentation. To have things serviceable and maintainable, you need to have adequate documentation. So if there's something that needs to be modified, that someone else can go in to look into that code and make those adjustments. So there's interesting, we need to figure out how we're going to be coping with the complexity of abstraction that has gone on and continue to mature on a lot of different fronts. And so the role of software has changed over the past 20 years. Most modern systems are dominated by software. And so a lot of the implementation is done in a software sense. And so we have cyber physical systems that there's a lot of things that are having to all come together. And so therefore, software engineering has become a full part of the system development. And so that is something that's important that has to be considered. And so this is a diagram that talks about these 3 terms. So we have systems engineering, we have software systems engineering, and then we have software engineering. So this is what they're quoting is the IEEE software system engineering process. And so we can see the system engineering V that's laid out here. And so the top part is where it's a mostly system engineering. And I would argue that all of this is in the domain of system engineering, but we're now getting a little bit more surgical. And so software systems engineering is how we're going to actually start with the requirements, start to architect the software design. And so then we slowly work down the system engineering V. Then we get into the software engineering and we do the detailed software design, we do the coding, and then we start to do the subsystem testing, then translating into, then we have a software system engineering component where we're dealing with the integration testing, the system testing, and then finally we go up to the top level, the system integration. So this is where we have system engineering. So there's hardware and software all aggregated together to make sure that everything works out as desired. And finally, there's the system testing. So this is the contents for the textbook I use in my software engineering course. And so Somerville is the author. And so there's 4 major sections that are contained in it. First, there's the introduction to software engineering. And there's a lot of things that really give you the basis of what is done in software engineering. Plus, there are some features that get into the advanced areas that I'll talk about in a minute. So software is a process, and so we want to be thinking about that. There are typically 2 main ways of thinking about development. You can either do things in an agile, and so you quickly come up with an update, and then you do some changes, and then you circle back and see how well things are performing against that. Just like everything else in system engineering, we have to be thinking about things in a requirement sense, and so that is definitely something that is there. System modeling, we've got a chance to get some familiarity with SysML. There's also something called the Unified Modeling Language in which SysML was derived from, and we'll get a chance to be talking about that a little bit later on the UML component. And so how do we get into the design and implementation of software? I'll have a chart that will show you a sense of how, from a software sense, the resources that are typically entailed for developing the software. We also have to do software testing. There has to be software evolution. All those things are important. There's various types of what I call ILITY, the dependability, the reliability, the safety, the security, the resilience. All of these are things that have to be considered in software. And then for software, advanced software topics, there's the concept of software reuse. Do you reuse a piece of modular code into a new system or not? So this gets into some of the component-based concepts. There's also things like service-oriented software, and so that is something that needs to be considered as well. So, and of course, there is the software management, and so you have to be doing project management, project planning, maintaining the quality, making sure that it's working properly, and then also dealing with configuration management. So that's just a little bit of an aside, thinking from the software engineering perspective. So this is the basis for how software is, and so you all are using your laptop. And so you can be thinking that for a computing environment, there is a hardware, there's a firmware that the software is loaded upon. And so the first thing is the operating system that is above that. Then you have the APIs, the application program interfaces, where higher level capability is loaded on top of that. That's something that has to be taken care of. And then we actually have the application software. We have the user interfaces, and so having a screen, a keyboard, a mouse, things like that. And finally, the user, the person that is trying to utilize all of those capabilities. Well, this gives you an idea of a computing architecture, and you can see that there's databases that are hosted on servers. And so this would be data servers, and above that, then we have the application servers. There is a variety and an ever increasing amount of things that are done on the cloud. And so having these application servers are where you would be engaging with a lot of resources. And finally, the clients that are actually using these capabilities. And so if we're actually building a satellite, for example, there is going to be some ways where we're going to have this cyber physical environment that needs to be considered. And so some of you within the various projects, you'll get a chance to be thinking about what is going to be composed with software and what is going to be more centric on the hardware. So the nature of software development, it can be categorized in roughly three areas. The system software, and this provides services to the other service. And so the enterprise level, the embedded software, it provides a function, services, or features within a larger system. And so going back to the satellite related example, there's something called a real-time operating system, or RTOS. And so it's constantly having to engage real time and keep up with where things are at. And so embedded software is one of the sweet spots that can be dealing with that. And then there's the application software that provides a service as a standalone system. So here is just a larger list of the software types: system, embedded, application, engineering, scientific. You can have a product line, a web-based, I mentioned that briefly. And then this other area that is just growing very quickly is this whole AI, the artificial intelligence, that is really changing how a lot of things are done. And so this is a kind of thing that from a software engineering perspective, you have to be quantifying what exactly you need to do for this capability. And you could be having one or more, maybe even all of those would be things that would be done. So here are just example of software dominated systems. And so I can be thinking of these three different types here, and I won't go through this whole table here. So for software embedded systems, you can have you automate complex subsystems to perform faster and more securely. So software embedded can be hosting a lot of that capability. You don't have to do that all in hardware. You can have a software intensive system, and so it can be manipulating masses of information to support decisions or acknowledge or acquire knowledge. And so say you have a lot of sensors, a lot of things that you're statusing, and so the software is key to making it all happen. You can also have data intensive computing systems, and so these are, say, you're having a cloud environment where you can have as much CPU power resources as you would need. And so you're solving complex problems, modeling complex systems by computation and simulation. So there's just a lot more detail here, but that's maybe just gives you some ideas. So what is the nature of software development? Well, we're reflecting a couple of things here. Systems that utilize software can be categorized in one of three ways. You can have software and embedded systems, which are a hybrid combination of hardware and software. And so what are you going to realize in hardware? What are you going to realize in software? And although predominantly hardware, these systems use software to control the action of the hardware components. Examples are most vehicles. You can think of any car, and Abby, I think you can relate with your autonomous vehicle that there's a huge amount of software. Spacecrafts, you've been hearing me talk about the James Webb Space Telescope, robotics and military systems all take advantage of software embedded systems. There's software intensive systems that consist of computers, networks controlled by software. And so these systems are used to perform virtually all of the system's functionality, including all automated complex information functionality. And examples are financial management, airline reservations, and inventory control. Maybe you've been in an airport sometime where you've heard examples when their reservation system, which is very software intensive, goes down. Literally everything stops because they've gotten to so intently used to using the software that without it, it's basically they can't do hardly anything at all. You can also have data-intensive computing system, which are large-scale computing resources dedicated for executing complex computational tasks. I know the national laboratories do a lot of things with very large computing environments, doing complex calculations, say for nuclear predictions, and so that would be an example. And so that would be something that Nathaniel might be thinking about with his project. So examples are weather analysis and prediction centers, nuclear effects prediction systems, advanced information decryption systems, and other computationally intensive operations. So there are some definite distinctions between hardware and software. Sometimes you can have a realization in one or the other, but this kind of gives you some of those subtle things that where you can be seeing one is actually better than the other, or we can have a very much a partnership where we can have a cyber physical realization of those. And so this is just some more details in this chapter that you can review and get some more perspective on that. So what is the nature of software development? Software has intrinsic differences from hardware. And so that's something that you want to be thinking about. So these differences include near infinite variability of software structural units. So you can conjure up all kinds of things in software. There's few commonly occurring software components. So you can take data structures and manipulate them, customize them for a specific application. So there's a lot of different possible software components. Software is assigned most critical functions. And so there's been a lot of type of capability that has been demonstrated. And so it's used inherently, like I mentioned, the airline reservation system as an example. Interfaces are more numerous, deeper, and less visible. Software functionality and size have almost no inherent limits. Software is easily changeable, so you're not having to pull out your soldering iron to put components together, but those interfaces still exist. Simple software changes may require extensive testing. Software often fails abruptly without warning signs. And so maybe you've heard the expression, the blue screen of death that Windows has had. And so those are gives you an example of a fatal interruption of performance that you're trying to make sure that that doesn't happen. Software is abstract and difficult to visualize. And so the hardware and software differences are found in structural units, interfaces, functionality, size, changeability, failure modes, and abstraction. So they are fairly different, but from a systems engineering perspective, we can still be using some level of common ways of thinking about them from that high level perspective. In terms of software development lifecycle models, life cycles of software-dominated systems are generally similar to the systems engineering lifecycle that we talked about in a previous lecture. While there is a number of lifecycle models, we can find four basic types. You can have a linear, an incremental, an evolutionary, and an agile. And so I've already mentioned this term of an agile. And so this is one of the things that for a large complex program, they may be deciding what is the best one that is beneficial for them. And it gets into the nature of the application and the operations. And so linear, having a sequential set of steps. Incremental is a repeated set of sequential of steps. Evolutionary, which is similar to incremental, except early increments are intended to provide functionality for experimentation, analysis, familiarization, and demonstration. And finally, agile is like you have this rapid development that you then cycle back and see where you are and make sure that everything works with that a little bit added level of total capability that you've made. There's a couple of different types of models. Here's one, a software development waterfall cycle. So you analyze, design, code, integrate, and do system tests, and finally you get into this operation and maintenance. And so you can be seeing this waterfall down, and then you can have feedback coming back, and so you have all of these different loops that occur for that way of thinking about the software development process. So for system engineering in the waterfall model, this just gives us some details that you can be reflecting back on this chart and looking at some of the objectives that are taking place for each one of those phases. And so you can feel free to review this a little bit later, but I'm not going to go into this in any more detail at this point. So there can be increments, and you can be seeing how over time you start the first increment. You can have some overlap with the second increment, and so you can maybe have 1, 2, or 3 increments that are going on in parallel, and gradually you lay one in at a time. And so we can see, so for this timeline, we can see that increment 1 and increment 2 are complete, but increment 3 is not complete by the end of what we're showing for this timeline. And so sometimes this could be like 1.0, 2.0, 3.0, or something like that of a release of a software package. And so we can have something that's functional at this point, so it can go operational. This next increment can have more capability and so on. Here is a spiral development, and so we can see for this case, we've seen a spiral before, but from a software sense, we're seeing that we're spiraling out. And so the software is getting more and more complicated, more and more robust, more and more complete. And so here we're just seeing these different quadrants that we go through as we do this spiral development. So maybe indicative of thinking of like what we are talking about for agile development. So here is a little bit more details about concurrent development, and the textbook talks about 5 different types of models. There's adaptive software development, extreme programming, something called Scrum. You can have feature-driven development, and something called Crystal. And so these are yet getting more details about how you're going to be doing your agile development. And so you can be seeing that there are some loops that are going on here. So does that spiral, does that agile approach, that current work, and finally you get to a point where it is accepted, and then you're able to integrate that, and then you can be going to the next increment of what you're doing. Okay, I have a couple of charts. This is going to be the first one, then I'll have some graphics, and I'll come back to the second part. So for the software concept development, we have the analysis and design. So the performance requirements for software embedded systems are developed at the system level and should be verified by software developers. Performance requirements for software-intensive systems should be established with close interaction with customers and users, and need to be verified by rapid prototyping. So we've talked about involving the stakeholders and customers before, where that's also true for software. They should not unreasonably stress software extensibility, and so that's something that you're going to be looking for. And then for software requirements are typically developing using 4 steps. So you're eliciting from the users and customers and stakeholders. And so this is where you have like the use case diagrams and generating the user stories, having that narrative slowly turn into requirements. Then there's the analysis and negotiation with customers. Maybe there's a little bit of go back and forth. Finally, you document those decisions and annotate what you're doing with the code, and then you do the validation. So there's needs analysis and feasibility analysis. That's something that needs to be part of this. And there's also the software requirements analysis and software embedded system components that have to be articulated. So here are some of the things that are going on. There's the user needs that you're trying to figure out. You then fold this into software requirements, and finally specifications. And so this is where we're starting to see, starting to get to the base of this triangle, and then getting everything documented and specifications. So there's You're trying to understand what it is that you're trying to do with the software, part of a larger system. And so this is a problem domain. Then we get into the solution domain, and what is the support technology that's going to be necessary to make it all happen. So here is just another way of thinking about the getting into the details of the software generation process. And so there's a requirements solicitation with the inputs from the stakeholders. Then it gets into the requirements analysis and negotiation, the requirements documentation, and the requirements validation. There is some feedback of this. So once you get to a validation, maybe you find out that, well, we need to tweak the requirements a little bit and then go through this with any delta that may have resulted from that, and finally get the outputs that is the result of this software generation process. So we have had a little bit of exposure to this idea of this modules. And so how balanced are the modules? You can be thinking about the functional layout. And so if it turns out that you have something that maybe one of these modules is not being used very much, maybe we might want to re-envision what's going to be in those set of modules. And so this gives you an example of tight coupling. And so maybe in some of your software, this is going to be easily done, but maybe there's other examples where it's just a linear flow. We do A, then we do B, and then we do C. And so it may still be showing enough complexity and a nice mixture of what's going on for each of those, but those are some things that you want to be considering. You can also have these functional flow, which we have seen with more of our hardware perspective. And here we can be having that functional flow where we can have decisions or the possibilities of how we're going to be doing things. And so we need to be doing, both of these have to be true. One or the other has to be true. You can have normal shipment or priority shipment, as we're seeing there. Or these things that you have to be doing both to take place. And so those are also some things that can be part of the software development process. You can have data flow diagrams that you can be seeing how things are going from one element to another. And this can be helpful for how you're going to be envisioning what you're going to be doing with your code. You can also be getting into a robustness diagram. And so now you're starting to visualize the code, if you will, thinking about what is going on, the inputs and outputs, the connectivity that have to be taking place. And so that just gives you some perspective on that. So this is the second chart. We showed the first one a few minutes ago. So this is a software concept development, analysis, and design, the second part. And so two prevailing methodologies for designing systems are structured analysis and design and object-oriented analysis and design. So have all of you had experience with doing some object-oriented programming? Maybe you can just do a thumbs up if that's something that you're familiar with. Using Java is an example of something that does that. There are other languages where something that's dated now, but just historically doing something like in Fortran, something like that, instead of doing something you might do with Java or C++, that might give you an example. Other methodologies include robustness analysis, which focuses on initial object-oriented architectures, functional class decomposition, and combined structured and object-oriented approaches. So here is this UML, this unified modeling language, and it supports all phases of the object-oriented development. And there's actually 13 types of diagrams. For SysML, we have 9, and those are the ones that we are using in our course with our project work. And each one of these presents different views of the system and is widely utilized. And so it is an industry standard as well as SysML. And so since this is focused on software Not all of those are necessary for what we're trying to do from a system engineering perspective. Well, we also have the thinking about the testing and the validation. And so this is what we're dealing with here. And so the engineering design phase of software development implements software architecture design and the computer instructions to execute the prescribed functionality. The phase produces computer programs written in a high-level language that is the source code, and subjects each program unit to a unit test before acceptance. So you have the source code, you compile it, you then do the engineering testing to see if it actually works. The program language must be suited to the type of software compiler available. And so the compiler is designed to work with a particular processor and computing architecture. It must conform with a design methodology and requires that staff experience with the language be available. So C, C++ are examples of workhorse programs that are still used, and as well as Java and other areas. But those are just some examples, and we'll see some tables in a minute. Prototyping and iterative development comes in two forms. So there can be purely exploratory, and it can be disregarded when its purpose is fulfilled. So that might be something, some kind of test software. It can be evolutionary, which is, and it is built upon. In a later case, high quality must be built in from the beginning. You can also have human-computer interfaces, which are critical elements in all software-intensive systems. So a person in the loop, those are things that need to be fleshed out, how individuals actually respond to things. And these types of interfaces usually are interactive graphical formats and may include voice activation and other advanced techniques. So these are just some examples of the languages. I mentioned Java, I mentioned C++ and C. Those are things. Visual is just historic, but there's still some legacy code that it doesn't make sense to refactor it. And so there can be some things that you might have a virtual machine that's running some type of Fortran code because it's still used for something. There can be the need for assembly language, which is a low-level programming that is close to what it is actually done with the computing architecture, just one level above that. And so that can be helpful for doing some things that are drivers for hardware, and where you're trying to have things operate very quickly and with very few resources. Here's just some more languages that are out there where you can be getting into some of the things, say for a GUI, say HTML. XML is a common way of dealing with data and mark it up in a certain way. Maybe some of you have done things with Perl. Python is another language that maybe is straddling halfway between special purpose and maybe a common computing languages. That's something that isn't listed in those charts that I'm showing right now. This just gives you a table of trying to give you have some of the distinctions between exploratory. And so maybe you're just trying to do the validation. You could use some or all of that source code that would eventually go into an evolutionary, where you have a spiral 1 or whatever, a release 1.0, eventually go to a release 2.0, things like that. There's a lot more rigor and formal acceptance for an evolutionary versus something that's just used as a disposable piece of software to help you with your overall development. So there is also various types of computer interfaces that are available. You can be thinking about that. Are you going to be using a GUI? Is that something that you want to have? Maybe some of you have using a command line interface that actually can be very powerful and very lightweight, and yet be able to do quite a lot. Touchscreen is getting more and more common. People with our cell phones and tablets, even laptops with touchscreens, all of that. Menus. And so these are just giving you some of those examples of things that are there that you want to be thinking about which one is the best one to be using under what circumstances. Okay, in terms of the software integration and testing, testing software systems involve many more test paths and interfaces than hardware and require special test points for diagnosing failures in their source. And so having a good and integrated development environment and testing environment can actually be helpful. Testing often requires end-to-end system level retesting after eliminating a failure. And so the Achilles heel for software versus hardware are different. And so end-to-end testing can be important to make sure that just because you got one piece of code that is working, but there may be something subtle that you're missing and you want to make sure that you don't miss it. Maybe you've heard the terms like beta software or alpha software. Alpha is like really, rough. Beta is getting closer to what it needs to be for release, but it subjects the new system to test by the customer and expose user problems before wide production, wide product distribution. So then we have the whole idea of software engineering management. And so this is a word chart, and I'll just show very quickly a couple of charts that will give a little bit more details. So we have the configuration management for software dominated systems is critical because software is inherently complex and has numerous deep interfaces. And so you want to make sure if there's some subtle changes that people know about it, and it's that configuration is documented. Since the software controls some of the most critical system functions, it tends to be subject to frequent changes. There's something called a capability maturity model integration, CMMI, and it establishes a 6 level of capability and 5 levels of maturity for an organization. The CMMI establishes KPIs for each level and provides a basis for assessing an organization's overall system and software engineering capability. Okay, so this is just a listing of the 6 capability levels. And so this is the first one that talks about that there are 6. And I apologize, there's a typo here. This should be saying 5, but I'm not going to go out of full screen mode at the moment. I'll do it in just a second. These are the maturity levels that the 5 that are associated with that. So that's a quick run through of software engineering. Like I said, I have a whole course that's dedicated to that, both getting a chance to introduce the concept as well as giving an example of working through a software development project. So we've had to deal with coping with complexity and abstraction, the nature of software development lifecycle models, software component development, the analysis and design, software engineering development, the coding and unit testing, the software integration and test, and finally there's the software engineering management. So let me pause and see if there's any comments or questions on that. You just want to give me a thumbs up if this is making sense to you. Okay, well, with that, I'm going to switch over to talking about our project work. And so I gave a little bit of an introduction on Tuesday to give you a perspective about sequence diagrams. And I was showing you this relatively simple one. And I'm going to show you this, and I'm going to go over to Cameo Systems Modeler and show you a sequence of, with that one, I can actually have it execute, and it will walk through these numbers here. And so you see that these numbers are related to one another. And so if you were to start to make these swim lanes and start to populate them, have a connection from one to the other, you're going to see it's going to create a 1. And so if you're still in this bar and you go to another swim lane, it's going to have a 1.1. Go to another swim line, it's going to be 1.1.1. And then we have things in the reverse. It starts to go up like that. So you can have it so it does it at those levels. But let me show you what things look like in Cameo Systems Modeler. And so actually, I'm not going to be showing this extra window. I'm just going to have it over here. I'm trying to make a full screen. Like with the activity diagrams that I showed you, like with the state machine diagrams, these are executable. And we can see that here we have some numbering schemes. And so we could just keep it all at the top level. So here we just have 1 through 9. And so this is trying to show the mission events for a launch, the spacecraft separation, the solar array deployment, the antenna deployment, and then it's ready to go operation. And so we can see some things here, like trying to give us an idea that there is a minimum and maximum time that's supposed to go between the spacecraft separation complete and when the solar panels are deployed. You don't want to have the batteries to lose their charge before we actually get them so that they're being replenished by the solar panels. So I'm just going to push this execute button here. And then what it does is it charges up this thing over here that I'm going to be showing on the side. I've also shown that slow down the animation speed, and we can just see how this works from one module to another. So we start with the power on. So the launch, the separation. I'm going to actually show this again in a minute, but have it a little bit slower still. So when you launch a satellite, you want it to be powered on. So it's going to be able to have this handoff and be able to readily do what it needs to be doing. So what this is trying to do is showing a sequence of passing of information, of having one thing being completed and another. A difference that we can see from this as compared to an activity diagram. Activity diagram was we can have things that are indicating a decision. So it's either true or false. And so we branch to one or the other. That's not something that we see here. We're just showing this exchange of information. Mostly the way this is shown here, it's showing information that's going from left to right. But there is one example here that's going from right to left. And so it's now on orbit. The spacecraft is ready to be operational. We can see that it's gone to that point. So let me pause and see if there's any comments or questions on what I've shown here. Okay, Abby, I saw your question. This is one of the reasons why I actually am using Cameo, because there isn't a way to do this executability with either the community edition or the modular, which is the version that I have. To have it be executable, you'd actually have to upgrade to well, I'm not gonna go to that mode right now. It's something that would be closer to what is required for the Cameo Systems modeler, that capability. So that's unfortunate. I know it is really a nice thing, and I'm trying to give you a sense that that is a capability that is going to give you that next level of trying to troubleshoot what you're trying to do with your system. So sorry about that. I wish it was available, but unfortunately that's going to be a shortcoming for that. Any other comments or questions that people have? Okay. There are several that I have from a former student that I include, and we have some level of complexity that you can have. And so maybe what I'll do after this is we can try and just do one on our own. But just to give you a little bit of a sense here that so we can see this general flow. It's going down from this is trying to show a control sequence. the passing of information from one to another, and then have it go back and going back to the control, ground control. And so you might see some overlap to what we did in a sequence diagram, which is okay. There is a little bit of overlap, but like I said, each one of these has a slightly different purpose, and so we want to be thinking about that. You can change some of these icons here. We've seen some examples of this. So this is a control. So if I go to the specification, this is shown to be a control. The default is when you don't change that that stereotype at all. I'm going to try. I haven't tried this, so let me see if I change this to control. What happens if it gives me otherwise? Yeah. So it has a slightly different icon for the different things, and so the stereotype is giving you a more specific way of considering what this swim lane, what this is actually doing. I'm sorry, this lifeline is doing. And then we can have this way of trying to combine fragments into maybe a term that we'll see in different areas of a package, if you will, or just we're trying to show that this is something that can iterate back and forth. So that's something that can be possible. So it can be challenging to pick up someone else's code and to make sense of that. So when I was trying to do some execution of these in the Cameo Systems Modeler, when it has these packages, what it does is it really doesn't quite work as well. And so I'm not exactly sure. There may be some issue with this. It just goes through this and it doesn't go within the inners of these packages. And so here we have a package within a package. But so this is a combined fragment. So that's what it's called in Cameo Systems Modeler. And here is just called a combined fragment. It's called the same thing. So that's good. This isn't necessary, say, if you're just trying to get something basic. And so maybe I'll just pull up another one. This is a little bit more straightforward. And so Kyle, this is dealing with a power scenario. And so maybe something like this might be easier for you to get your arms around to start out with something like that. Okay, let me go ahead and try and create a new one. And so if you guys haven't already started to play with this, maybe this will be helpful. So I'm just going to do a blank one. And like I said, on Tuesday, I'd recommend that you do this real time. So some of these diagrams, this is another shortcoming of visual paradigms. You can see how it doesn't show you the SD that's in front. If you go look at Cameo, all of them are done according to the specification. And so this is one of the reasons why I typically just start my diagram names with whichever one of the 9 SysML diagram types are there to try and make up for that shortcoming to make sure I know what it is. I'm going to keep on the satellite theme. So I'm just going to call this a satellite control sequence. Start with that. So do a lifeline. So call it ground. Do another lifeline. Call it satellite. Do another one and call it call it the satellite computer. And then do finally one more, call it the sensor. So I want to have a connection between this. So a message to another lifeline. So I'm going to do that. I'm going to click on the satellite. So it created that line. It created a little bar here. I could annotate this with a name if I wanted to. I'm just going to leave that blank. And so if I want to have it connected to the same little block here, do that to the next one. So like computer. And then okay, so what does this mean? And so that's one of the things that I can be thinking about. Okay, so they say this is how I'm trying to command my sensor. And so there has to be this continuity of the sequence that goes from one to another. And then, so if I wanted to then create a response, well, let's say I'll do this one first. And so I'll say something like do measurement, and you can make these a little longer. Go back to the satellite computer. Back to the satellite. And back to the ground. So that just gives you a rough idea of what it can look like here. Let's see if I, so what I did, maybe it's a little bit easier to divide these up to help us to, so you can actually make these into individual things here. So let's change the naming convention, the numbering convention here. So I have say the setting of the command, an operation. And so I could also, Well, let's just work with this basics. Are you guys following what I did there? Does that make sense? Why don't you give me a thumbs up if you're following along with what I did there?
How how'd you do the change number thing? Can you show that again?
How did I change numbers?
Mhm.
What I did is I broke these things up and it has like a numbering convention that it does on its own. So um, like I could split these up. Uh, yeah, that's not what I want. So let me do like another thing that I'm going to do. So maybe I'll try and so hey, I'm gonna split this up here. So this is what Nathaniel, this might be helpful. So you can see how this is related to this item here. If I split this changes that numbering. And so I don't, this is not related to this. I'm going to try and do something different here. You can actually shrink these if you want. So, okay, that's what I want. And so, a lot of times what happens with large satellites, like the James Webb Space Telescope, is they would have like a telemetry and command, a low data rate where you can get some basics things. And then they have a high data rate that's associated with the actual payload itself. And so this would be like another path in which you can be doing that commanding. And so this is like an example of what I'm trying to show here. And so that would be another possible way of having something that you're trying to annotate. And then we can have a response that's going back from the ground directly to the sensor. All right, well, let me pause and what I'm going to do is I'm going to stop sharing my screen.
I have
And
one more question too. When you read this diagram, is time just like moving from top bottom?
so basically, each one of these is a sequence flow of information.
Hmm.
And so this is like one example of an exchange of information. And below down here, we see another example of what's being laid out. So yeah, you could say from top to bottom, um, you anything that needs to connect with something else has to be annotated with these connections that I'm trying to show you. Does that make sense?
Yeah, thank you. That clears it up.
All right. Well, you guys have some feedback to me. How do you think this might be useful for your project? Or if you want to be sharing your visual paradigms, we can also do a little bit of go back and forth with that. To spend a few minutes here to do that now. Any of you want to share what you have, or you want to at least have a conversation about what you would like to share, what you would like to do?
I can share, but it's on my phone, so I don't know how I can share like the.
Yeah, if you just go to Zoom, and on the bottom there's a green button with an up arrow.
Oh yeah, but
You can share
because
your.
I have Visual Paradigm on my laptop, but I have the Zoom on my phone. But I think I
Oh,
can like change the camera to show it.
yeah. Well, okay, yeah, that gives me an idea what you have there. So yeah, I think that's
Can
a
you
little bit
see
hard
it?
for me to read, but I can see the
Oh,
general nature of what you have with your diagram, and I think what you're doing is great. And so you can see, like, what I did is I created one sequence, and then I actually put in another one. Is as you start to think about what you're trying to do, this can be like a scratch pad, if you will, to be annotating some of the things that you find are important when you're trying to figure out the the system perspective of your design of what you're trying to accomplish. But Abby, I think it looks good.
okay. And it's like specifically for communication.
It's for sharing of some type of information. Um, let me close out this project, and I can show you something completely different here. I'll just quickly scan something. But let me see if there's anybody else that would like to share. Well, while you're all thinking about that for a minute, I'll just show this briefly, and then so what I'm showing here, this is like another project, a paper that I just got approved for publication. And so this is something of how a bacteria actually does its sensing, and then passing that it has a sense detection to different parts of what is part of that bacteria. And so they have the receptors, are called chemoreceptors. And so this is what starts to happen. It passes on that information, and based on the concentration that it's in, it either starts to enhance or detract from its sensitivity. Just like you can think of like your eyes, if it's really bright, your eyes get more accustomed to that bright light. And if you were to go from a light to a dark room, you would notice that it takes your eyes a while to adapt. Your hearing does something similar to that, to get used to loud or very low level of noise. Well, this is just another type of sensor that we can see with a bacteria, and it does have this general flow. And so there's a way of, they're not using electrons to pass information, but there is a passing of that signaling information, and then a response to that signaling information that actually takes place. So these are just several things that I was annotating to be showing here in a couple different manners, maybe just to give you yet another example of what this could look like. But yeah, in general, it is meant to be some kind of information, or that's being passed, or maybe something physically that's being passed of one form or another. Any other comments or questions?
Do we need to specify like what type of information is being passed? Or just like say that?
That's going to be, remember, with each submittal, you're also having a little narrative of what's going on in that diagram. So you want to have maybe some things that's going to give you some tips by just looking at the diagram itself, but you can also annotate that further with the text write-up that you'll be doing along with that. Okay.
Okay, thank you.
Any other comments or questions? Kyle, does that make sense? Were you able to follow along with what we were talking about there?
Yeah.
Yeah, I hope you were having visual paradigms open and giving it a go, because I think it'll make it a lot easier and actually a lot more fun. Jonathan, any comments or questions?
No, that makes sense.
Okay. All right, well, I'll let you guys have some more fun with it. You can be actually part of system engineering. I think it can be a very creative process. And some of these things that we're doing can help you to flesh out and maybe see some things that you weren't seeing initially, some additional details that needs to be worked through. So anyway, Lord bless you all. I'll look forward to seeing you next Tuesday. And by the way, we're going to have some visitors, at least for part of our lecture. There's a junior college that is interested in finding out more about APU, and they're going to be sitting in for a couple of classes. And our class is one of the ones that they're going to be getting a chance to sit in. So I look forward to sharing you all with these folks and letting them meet you as well. Okay. God
I have,
bless everybody.
I have one more question. Should we
Sure.
have a couple diagrams or just one?
I would say at least have one, but I would challenge you to try and make more than one. So say at least having two. Start to determine what are the examples of different types of sequencing or messaging, things that need to actually be done to make your capability that you're modeling work. Okay.
Okay, sounds good.
All right. Thanks, everybody. Take care now.
Thank you.
Thank you.
Thank you, Professor.
Sure thing.